Okay, so hey, welcome to Module 3. Our first section is 3.1, Getting Ready for a Pool Party, and this is a developing understanding task. Now, what we're going to do is we're going to be given some situations that you see in the chart below, and you're going to be asked to create a graph. And with remote learning, if we were in the classroom doing this live, I'd put you guys in groups and you guys would all create your own graphs and they'd look rather different. And then we'd present, we're doing this remotely, so we're going to present a graph together, but I'm going to take that opportunity then to really review the material we've covered already and add some new stuff today. So I have a piece of graph paper in the Google Classroom that I would like you guys to print out so we are all working with the same original graph. And let's have a little fun today. So Sylvia has a small pool full of water that needs to be emptied and cleaned, then refilled for a pool party. During the process of getting the pool ready, Sylvia did all of the following activities, each during a different time interval. And we're going to come back to these activities one at a time. But right now, let's see what they want us to do. So I'm going to go over to my hyperlink right here, number 1. And number 1, sketch a possible graph showing the height of the water level in the pool over time. Be sure to include all of the activities Sylvia did to prepare the pool for the party. Remember that only one activity happened at a time. Think carefully about how each section of your graph will look, labeling where each activity occurs. All right, this is going to be really cool. So here is the graph that I gave you guys in Google Classroom to print out, and I think I may have already scaled it for you and labeled it. I'm not sure though. So let's start by going, here, we can start right here. Sylvia has 120 minutes to get the pool ready. All right, so let's kind of set up this graph right now. Let's start with labeling our horizontal axis right here. All right, and on that horizontal axis, what are we measuring? Well, we have 120 minutes, so this is going to be time in minutes right here. All right, and then you've got to decide, let me see, we need 120 minutes total to get this done. So how are we going to scale the horizontal axis? So it looks like I'm going to go, each hash mark is worth 8 minutes. So every hash mark is 8 minutes because we're going 8, 16, 24, 32, and so on. All right. Now, I also need to know how deep this pool is. All right. Now, this is one of those littler kiddie pools, I know the picture looked like a pretty cool pool, but there's not much to it right here. All right. Oh, yeah. And we did get our 120 minutes in right there. So Sylvia's pool is 24 inches deep, 2-footer. All right. So we've got to get our hash marks in inches to get to at least 24. So with that, the vertical axis is going to be the depth of the pool. And I probably used inches. I did. So H of T in inches. And let's see how we scale to get that done. All right, so I'm going each hash mark here 2 inches. And that gets me to that 28 inches right there. And that's the starting point right there. 24 inches deep. There's where we're going to start our graph. Okay, all right. So let's go to the activities and see if we can graph what's happening here. So to the activities, I hope my hyperlinks work well. Oh, look at that. Okay, so when Sylvia was getting this pool ready for the big pool party, the first thing she did was she removed water with a single bucket. All right, so let's graph what that would look like. So I'm going to go to the graph over here. All right, now the water in the pool, the height is 24 inches right now. Now, if we remove water 1 bucket at a time, what's going to happen? Well, the water level will slowly lower 1 bucket at a time. All right, and we get to determine, how much it lowers based upon we're picturing the kiddie pool and maybe a 5-gallon bucket. So here's what I'm picturing right here. 24 inches, 1 bucket, it would drop down to, oh, and a little note, for 16 minutes, Sylvia removed water with a single bucket. So we're going to remove this water with a single bucket, 1 bucket at a time for 16 minutes. So we're going to go from here to here on the horizontal axis for time. And now picture the water just dropping. So it would do something like, I don't know, that right there. That's my first bucket. So it looks like 24 inches went to 23 inches, and then we're going to go to 22 inches, and then we're going to go to 21 inches, and then we're going to go to, oh, let's see, 20 inches, and that is the first 16 minutes right there. Man, so Sylvia and my problem right here, she must have had to get a bucket and then walk somewhere to dump the bucket, okay? Because that took a little time to do 1, 2, 3, 4 buckets, all right? So Sylvia's just not on the deck just taking a bucket and dumping it right outside the pool. All right, and again, we get to decide what's happening here. All right, so let's see what else happens now. Let's go back to the activities, all right? So next, Sylvia is going to drain the water with a hose, the same rate as she's going to fill the pool when she's all done here. All right, so I'm going to go back to my graph. All right, now, you know what I think? All right, if Sylvia is going to drain water with the hose, then first she has to, I know like when I'm doing this kind of stuff, I have to go to my shed and find my darn siphon hose. All right, and that takes time. So while Sylvia is looking for the siphon hose, that water level is going to stay the same for an interval of time. So for 16 minutes, Sylvia searched for her small siphon hose. So that means the water will stay at 20 inches from the 16-minute mark to the 32-minute mark. Oh, how cool. We're right there. Now, during that 16-minute interval, Sylvia searched, found the hose, got back to the pool, and I don't know if you guys have ever siphoned water out of a pool, but then you put one end of the hose in the pool, you get on the other end, you suck the water and get it started, and make sure the other end of your hose is lower than the end of the hose that's in the pool, and it will start siphoning at pretty much a constant rate. So then we search for the hose, and now for 8 minutes Sylvia drained the water with her small siphon hose. So this is only 8 minutes, so we're going from 32 minutes to 40 minutes right there, and it's going to drain at a constant rate. Now watch how I graph this, and here we are right there. Now notice something. Okay, for the first 16 minutes when Sylvia was emptying the pool 1 bucket at a time, do you see how the graph is discrete? And then when Sylvia is searching for and setting up the siphon hose, the function is constant and continuous, 20 inches. And then when the pool begins to drain with the siphon hose, this is continuous. Water is flowing out of the pool, and water flows at a continuous rate. All right, so that's it. Have we accounted for everything so far? So what's going to happen next? Let's get back to the activities. All right, well, what's the third thing that Sylvia is going to do? Oh, Sylvia and her 2 friends then removed water with her 3 buckets. So 2 friends have arrived early for the pool party, and they're going to help Sylvia get set up. And Sylvia just happens now to have 3 buckets. So they're all going to start pulling water from the pool, 1 bucket at a time, but now they have 3 of them. All right, let's see what that would look like. Well, I think that this part of the graph, let me write that down. Oh, a little note about the water draining first, though. At what rate was the water draining? This is pretty important. All right, so, well, I hope you guys are beginning to realize that a slope is a rate of change. All right, so, you know, if you picture a slope triangle right here, What's my rise and what's my run? Okay, well, we dropped how many inches while we were draining the pool with the siphon hose. We went from 20 inches to 12 inches, so that's minus 8 inches. And then how long did that take? Well, we went from 32 to 40, so that was what, 8 minutes? So my rate is going to be, and that's a slope right here, it's going to be negative 8 inches, and that took 8 minutes. Or that's going to be negative 8 over 8 is negative 1. That would be negative 1 inches per minute. Negative 1 inches per minute. Very cool. Now let's get to the 3 buckets going on right here. So 2 friends arrive for the party. So Sylvia pulls the siphon hose and they begin emptying the pool for 16 minutes, 3 buckets at a time. So now this part of the graph I think would be discrete again, because they're doing it buckets at a time, 3 buckets at a time. And I'm going to try to make this really realistic. So when it was 1 bucket, we dropped what? 1 inch? So now we would be dropping 3 inches at a time for, and how far? For 16 minutes. Let's see how we did here. Yeah, there it is. Look at that. We went from 12 inches to 9 inches. And then we're going to get down here, right there. And then they do it again. So we're going to drop to what? Right about there. And guess what? 1 more and the pool is empty. Right there. The pool is empty now. And this is the discrete part of the graph again. Okay? Because we're doing it 3 buckets at a time. Boom, boom, boom. And the pool is now empty. So I wonder what they're going to do when the pool is empty. Do you think they might be cleaning it up a little bit? Let's get back to our activities. All right. Oh, it's break time. All right. We're tired, man. We've been 1 bucket at a time, 3 buckets at a time. So let's get back to our graph and talk about what does break time look like? Well, the pool's going to be empty. And it's going to be empty for ever how long they're going to be breaking. So let's see. The pool is empty and the girls take a 16-minute break. So where are they at right here? They are at 48. That would be, and then is that 56 right there? And then we're going to go 16 minutes. So that's going to be a break to right there, which is 64 minutes. That's the 72-minute mark right there. Okay. Break's over. Okay. So there we go. The pool was empty for, what, how many? 16 minutes right there. Now what are you going to do? I know what I think I would do after I emptied the pool. Yeah, clean the empty pool. Okay, so let's get back to our graph. And when we're cleaning the pool, it's going to stay empty. So the girls spend 24 minutes cleaning the pool. Oh man, they have this pool really clean. So 24 minutes, that would be to what? The 96-minute mark right there. The pool is still empty while we're cleaning. All right, I think we've accounted for that. And notice that when the girls were taking a break and then cleaning the pool stayed empty, so it's constant and continuous. The water level of the pool from this time to this time is at 0 inches. Okay, well, what do they have left to do? They better fill the pool back up now that it's clean, so let's find out. Filled the pool with a hose, same rate as emptying the pool. All right, so let's get back here now, and let's think about this. They emptied the pool at -1 inch per minute. That means they're going to fill the pool at 1 inch per minute. All right, so you see how we went -8 and then 8? Now here, wouldn't we go +8 and then over 8 like that? Let's see. After the pool is clean, the girls hook up the hose and fill the pool at the same rate that Sylvia drained it with the siphon hose. So I took my slope triangle and I just reflected it over a horizontal line, and I went up 8 inches and then over 8 minutes. And there we are. And let's do that again, and we'll do it as many times as it takes until the pool is full. So let's go. How many hash marks is that? 1, 2, 3, 4. So I'm going to go up 1, 2, 3, 4, and over 1. Not full yet. 1, 2, 3, 4, and over 1. And I think at that point right there, the pool is full. And now let's think. When we're filling the pool with water, water is flowing continuously. So this is going to be a continuous line that goes through these 4 points. And there we go. The pool is now full. So now check it out. This is really cool. We are discrete and decreasing. We are constant and continuous. We are continuous and decreasing. And then we are continuous but discrete. And then we are constant and continuous. And then we are not constant, we are increasing and continuous when we fill the pool. All right. So, and Sylvia's pool is ready for the party. And you see this young man right here? If my mother saw this diving into the 2-foot pool, my party would be over. So we better put up a sign. No diving into the 2-foot pool. There we go. I hope that was fun for you guys. I know I had a ball. All right, so number 2, create a story connecting Sylvia's process for emptying, cleaning, and then filling the pool to the graph you have created. Do your best to use appropriate math vocabulary. Well, really to create our graph, we had to create a story. We had to understand what was going on and what was happening to the height of the water in the pool as time was going on and on and on and on. All right, so let's take this opportunity to really clarify our story, but also let's use some not only math vocabulary, but math notation to set us up for Module 3 in Integrated Math 1. This is going to be really cool. So, our first thought is this, okay? We labeled the horizontal axis for the input, and the input was what? Time, right? Because we were cleaning and then filling the pool, emptying, cleaning, then filling during time in minutes. So time in minutes, okay? And then we were also told that the pool was 24 inches tall, so Sylvia's pool is 2 feet deep, so that's why we labeled the vertical axis with our dependent variable h of t in inches. So the vertical axis is labeled with my output h of t in inches. Okay, now where did we start? For 16 minutes, Sylvia removed water with a single bucket. So that is this part of the graph right here. As the water was being removed 1 bucket at a time for 16 minutes. So let's talk about what that means. H of t is, well, this is decreasing. There's a negative slope right there. And it is, well, isn't that a straight line? So it's linear, all right? And then finally, that's just a scatter plot, so it's discrete, because we're moving that water out of the pool 1 bucket at a time. Now, let's just talk about the domain for this part of the graph right here. And remember, domain, if we're talking about a discrete function, it is just every x value for each one of these points right here. So t is in. So in a discrete function, we use set notation. That means birdie brackets. And what's our first x value right there? That would be an x, or t I should say, is 0. And then how far did we go before the next bucket? Every 4 minutes, right? Because it's 0, 4, 8, Okay, so let's go 0, and then at the 4-minute mark, and then at the 8-minute mark, and then at the 12-minute mark, and then at the 16-minute mark. So that's how we express the domain for this part of the function right here. Very cool. All right, then what happened? For 16 minutes, Sylvia searched for a small siphon hose. All right, so there, that part of the graph is right there. It's staying constant. So let's talk about this now. H of t, we're no longer decreasing, we are constant. This is a horizontal segment right here. So we're constant. All right, and it's also not a scatter plot. It's a segment that's continuous. For how long? For 16 more minutes, right? So for t in, well, we were at the 16-minute mark right here. So now, because I'm continuous, I can't use the set notation now. I've got to use interval notation. So this t value is at 16 minutes. And then we go continuously until we get to, and that was what? 32 minutes right there? So here's my notation. T is in the closed interval from 16 to 32 minutes. That means T is everything from 16 to 32, including 16 to 32. So here's your notation for a continuous function, and here's your notation when you have a discrete function. This is set notation, and this is interval notation. Start learning the difference. All right. Well, after Sylvia found the hose, she siphoned the water out, and it drained at a constant rate. Okay. So, and I shouldn't say constant, because constant implies horizontal, but now this is a constant rate of change right here, which makes that linear. So then for 8 minutes, Sylvia drained the water with her small siphon hose at a rate of 1 inch per minute. Okay, so now let's look at this part of the graph right here. Again, it's decreasing, and that's a straight line segment, so it's linear. Okay, and it's a line segment, so it's what? It's continuous again. So now I have to use my notation, my interval notation, for my time during this part of the graph right here. So t is in, all right, and I look, all right, my t value can equal that number, and my t value can equal that number, so I'm going to use brackets. And then what is this t value? 32. And what is this t value right here? That'd be 8 minutes later. That's 40. So t is in the closed interval from 32 to 40. Again, that means t can be 32 minutes to 40 minutes, including the 32 and 40. Everything in between. That's why they call this an interval of numbers. And again, when you're continuous, we have to use interval notation. Okay, then now I think, didn't Sylvia's friends arrive? So 2 friends arrive for the party. So Sylvia pulls the siphon hose, and they begin emptying the pool for 16 minutes, 3 buckets at a time. Okay, so that's this part of the graph right here. Okay, all right, so h of t is, okay, the function is, well, we're still decreasing. But now we are not continuous, we are discrete again, because they're moving the water 3 buckets at a time. Oh, and it's linear, that's a straight line, and discrete. There you go. Now, because we're discrete, we go back to our set notation like we did above. Except all we have to do is list our t values. So t is in, birdie brackets for set notation. And what was my first t value right there? It was 40. And then we're at, well, let me see. That's 4 minutes, 44, 48, 52, and 56 minutes. So we're at the 56-minute mark right there. Okay, great. All right. Now, the pool was empty, and the girls took a 16-minute break. So this is this interval right here, 16 minutes. So what's going on with this graph? H of t is, well, it's not decreasing anymore. The pool is empty. It's not increasing yet. So this is what we call constant when we're horizontal. It's just a constant function during that time interval. And because that's a solid segment, it's continuous. Constant and continuous. So now we've got to use our interval notation again. So t is in, and I can equal that t value, and I can equal that t value. So I'm going to use brackets. And what is that t value right there? Was it a 52? Let me see. No, that was a 56. Right? Yeah. And then we go to 64. And then we go to, isn't that a 68 right there, I think? Let's find out. Let's see. Now, every hash mark is 8 minutes, so that's 64. No, that'd be 72 right there. So 56 to 72. So t is in the closed interval from 56 to 72, which means t can equal 56, t can equal 72, and t can equal anything in between those two numbers right there. Very cool. All right. Then the girls spend 24 minutes cleaning the pool. So again, while they're cleaning the pool for 24 minutes, it's still empty. So h of t is, and again, that's horizontal, so we're still constant. It's still continuous. And now I just need that time interval. So t is in, and again, t can equal that value and that value at the 96. So I'm going to use bracket, bracket. And then what is this t value right there? That would be, what? Is that 72? 72 minutes until the 96-minute mark right there. So t is in the closed interval from 72 to 96. One more time. That means t can equal 72 minutes, t can equal 96 minutes, and t can equal anything in between those values. Everything, I should say, in between. Continuous. All right. After the pool is clean, the girls hook up the hose and fill the pool at the same rate that Sylvia drained it with the siphon hose. And that's where we had this positive slope of 1. So let's talk about that part of the graph. All right. Now, for the first time, we are what? We're increasing now. The height of the water is increasing. And it is continuous because water flows continuously, and it's linear. So linear and continuous. And what is this time interval? It's from the 96-minute mark to the 120-minute mark right there. So t is in, and t can equal 96, t can equal 120. So I'm going to go bracket, bracket, 96 to 120. There we go. There's our story with a lot of algebra notation too in there. I hope you guys are enjoying this. Now, does your graph represent a function? Why or why not? So we need to know, what is the definition of a function? I believe I called it a function a few times. All right. And there's a very simple definition. A function implies every input x, or in this case we're using t's, has one and only one output y, which we're talking about y is h of t here. Okay, so now there's an easier way to picture that if I have a graph already. We do a thing called the vertical line test. Now, if wherever I draw a vertical line across this graph, it will only cross the graph at one point, then that would be the graph of a function. So, or h of t passes the vertical line test. And this graph would pass a vertical line test. There is nowhere where I could draw a vertical line that's going to cross that graph at more than one point. So, our graph represents a function. Okay, so this was just an introduction to all this notation and a lot of review on discrete, continuous, linear, increasing, decreasing, constant. This is a great little activity. I hope you all enjoyed it. Now I'd like you to finish the Ready, Set, Go for 3.1, and you guys have a great day.